Let us continue with geometrical application of definite integral. Once again, the main idea is, if the problem is too complicated to consider it in one step, we divide the problem into a large number of small elements, small contributions. We compute the problem for one little element, and then integral takes all of these contributions together. And this works for a question like that. We want to find the volume of a solid of revolution. What does this mean? Consider a positive continuous function f, which has in the xy plane a graph like that for x running from a to b. And now imagine that this xy plane is embedded in a three-dimensional space, x, y, z. And now in this three-dimensional space, this curve is rotated around the x-axis. So a body like that is formed, and this is called a solid of revolution. Revolution means rotation around the x-axis, and solid means a solid, fixed, hard body. And we want to find the volume of this body, of this solid of revolution. Well, and the main idea is, if this is too complicated, then we cut the solid into a large number of thin slices. Each slice can be considered as a cylinder. If we have a cylinder like that, then the volume is the base, which is pi r squared, times the height h. This time, one thin slice looks like that. Here the axis was vertical, here the axis is horizontal. But the volume is still the base, pi r squared times height. So now, because this is small, we will call it dV as the element of the volume, differential if you like. And this is pi times r squared. R is the distance from the center to the perimeter. Here, the distance from the center to the perimeter is y, and y squared, because we have r squared. And what is height? What is the thickness of this thin slice of this cylinder? This is dx. Well, and if we integrate, then the total volume is integral from a to b of pi y squared dx, where y is the function that defines this curve that is rotated around the x-axis. So this is the formula to compute the volume of the solid of rotation given by the rotation of this graph of this function. Let me give you an example. If we have the function y is sine of x for x between 0 and pi. Imagine that this is in the x, y, z in the three-dimensional space, and this curve is rotated around the x-axis and forms a body like that. So the volume will be integral from 0 to pi of pi r y squared. Y is sine, so we have sine square of x dx. And this can be computed. Sine squared, well, first we can factor out pi. Sine squared can be written as 1, if you consider sine, then sine squared looks like that. And this can be computed as 1 minus cosine 2x half dx from 0 to pi. And this is easy to integrate. We can factor out 1/2, and we have pi half, and integral of 1 is x, and integral of cosine is sine. But when we differentiate, we multiply by the derivative of the inner function, which is 2, and when we differentiate, and when we integrate, we divide by 2 from 0 to pi. But sine at 2 pi is 0, sine at 0 is 0, so this fraction contributes nothing, and we have x, which is pi times pi half, which is pi squared half. We can generalize this result. This sine of 2x is always 0 when the argument 2x is an integer multiple of pi. So when the limits are integer multiples of pi half, this fraction gives nothing, and that means this contributes nothing. And we can say that integrating sine square or cosine square in nice limits, that means in limits that are integer multiples of pi half, is equivalent to integrating 1/2. But even if you don't like this trick, this is how to use the formula to compute the volume of a solid of rotation. Let me give you another example. If we have a function x squared and the interval, say, from 0 to 1. So we have this nice little piece of parabola, and imagine this is in the 3-dimensional space, and this parabola rotates around the x-axis, so we form a solid of rotation like that. And then the volume will be integral from 0 to 1 of pi y squared, but y is x squared, so y squared is x to the power of 4 dx. We can factor out pi, and we have x to 5 divided by 5 from 0 to 1, which is pi over 5. And we have the result, the volume of the solid of rotation when this curve is rotated around the x-axis.